Hello everybody and welcome to the KMC Controls webinar on PID Loops. Really happy to have you all here with us on this awesome Friday. Hope everyone is doing well and is very excited for this awesome topic. Today, backed by popular demand, we have the building geniuses, Eric Kruder, Kevin Mooney, and Gene Stutzman all here to give us some great information, a lovely PID loop presentation, and we're going to dive into a little bit of demonstration as well. Just a reminder, as usual, you feel free to give us your questions during the webinar. We record all of these questions and they help guide our future webinars. We'll try to attend some of them during the webinar, but if we don't get to them during the webinar, don't worry, we'll try to address them after the fact and we'll be sending you correspondence. So a really quick poll before we get started. We want to know, how familiar are you with PID loops? So let me launch that poll here and let's get a pulse on that. All right, thank you guys. So it looks like most of you are somewhat familiar with PID loops, but you're kind of looking to dive in deeper. So we're going to try to give you that good information here today that you're looking for. So without too much of a further ado, I'm going to go ahead and hand it over to the building geniuses to show us about PID loops.
Morning, everybody. This is Eric Kruder speaking, and as we get the presentation fired up here, let's talk first about what we're going to run through today, a little agenda. First, we'll talk about the definition and some of the terms that we use as we either teach or describe or help people with their PID loops. We're going to talk about how the loop value is calculated, look at a little bit of math, but really what each component is doing and how it might affect the loop output. We'll talk a little bit about some tips of loop tuning, and then just a real quick list of where to start and what to look for. After that, we'll look at a couple loops we got here running in our building at the factory, and what you might do and connect to get started. So first, just a quick idea what some of the definitions and vocabulary related to loops are. A PID loop is also called a control loop. It's really a strategy or a calculation that's used in many type of processes. In building automation system, the loops are designed to maintain any type of medium in that building: temperature, pressure, flow, or other physical properties that that controller is trying to manipulate and adjust to maintain comfort and efficiency. For a closed loop, which a PID loop would be, we need some sort of feedback or input to the loop, and we need a reference to compare that to. So commonly that would be room temperature and set point. It could be a loop water temperature or a static pressure that we're feeding back and comparing to a set point. Once we have that comparison, we're going to run it through a calculation, which is the loop object, and we're going to supply that as an output. Many times in our controllers, and a best practice would be to write that loop output to a variable, and then you could reference that variable in Control Basic or decide to plumb that directly up to an output from there. So looking a little bit inside, again, we need an input, so we need to be sensing something, condition, temperature, flow, whatever the condition of that process that we're measuring. We're going to compare it against a reference or a set point. That loop is going to respond. It's going to try to do something to maintain that set point and adjust things along the way. So we're adjusting a damper or a valve, an SCR, something that's going to manipulate the medium that we're sensing. The important thing here to remember is we want that closed loop, so that way the loop knows if what it's doing is being effective or not, and can change the math or the response based on that condition. So as we look at the calculation of how that loop value is determined, there's 4 components that you'll see that all get added together to produce that loop output: proportional, integral, derivative, and bias. So all work off the comparison or the error that's generated between the set point and the reference or the input. And depending on how you have those loop constants set, one piece of the PID loop might be responding more than another. But again, it all depends what your system is and what you're trying to do. So let's look a little bit deeper at each of these constants so we get an understanding of what they're trying to do. Proportional would be the most common. With proportional, the proportional term provides a linear gain to the loop. So the greater error I have, the greater the proportional term or constant gets applied to the output. One thing we try to emphasize, a way to think about this, think of it as a throttling range. So, if we have a room temperature of 72 and a set point of 74, we have an error of 2. If I have a proportional of 4, that would get me a 50% output. For these, for this setup, if I had an error of 4, I would get 100% loop output. Again, the greater the error, the greater the proportional term as it's applied to the output. Moving to integral then, the integral term provides a correction that is based on the error over time. In effect, this should drive the steady state error to 0. If I'm using just proportional control, say my loop output got to that 50% and I'm maintaining a temperature to like 1 degree against my set point, the loop's just going to stay there, because again, it takes some error to prop up that proportional band. Ideally, we'd like our error to go to 0, and that's what the integral is going to do. It's going to keep adding a little bit of loop output over time to try to bump that output further than the proportional band could do on its own, and that should drive my error down to 0. So if you talk to a KMC person or a controls person, a lot of times you might hear integral term referenced as resets or repeats. This comes from the concept of repeating the proportional band every integral period. So 4 repeats per hour or a number of repeats per minute, depending on what we're trying to control. But the two big concepts with integral, again, is I'm adding a little bit of error to the, or a little bit of output to the loop over time, and I'm trying to drive that steady state error down to 0. So the last few terms to know when we're talking about PID loops would be a derivative. This is called rate in some systems. Derivative reacts to fast changing errors, and it really works to try to dampen or slow the response. Being that most processes in our building automation systems are generally pretty slow, we don't commonly see derivative used. And if we start introducing derivative without tuning our other properties, it's going to give you some responses that may be confusing or hard to tune. So generally we say stay away from derivative unless you're doing something that you know is a very fast changing medium in your building. Bias is another term that is added into the control loop. Bias offers a constant offset to the loops, and usually we only see bias or only recommend bias if you're using proportional only systems. Here again, if I can add a little bit more output with the bias instead of proportional only, maybe I can reduce that steady state error without having to put any integral action in. And lastly, the last real term that affects our PID calculation would be action. We need to decide if this loop is going to be direct or reverse acting. Direct, think of a cooling loop, is going to increase the loop output with a positive error, and reverse again is just opposite of that. So increasing loop output with a negative error. So at the end of the calculation, after we know each of our individual terms, we have a proportional term, an integral term, a derivative term, and a bias term. We're going to sum all that together, and that becomes the output of the loop. I will mention that in KMC products, the loops are smart enough to know that if I have 50% proportional and my integral maybe calculates to greater than 50, we're automatically limiting that integral term to prevent any windup that might be happening in that loop. So let's talk a little bit about tuning our loops. Now that we know all the individual components, where do we start? When we're going to tune a loop, we want to start by setting up a process to monitor what's going on. This could be using Connect to either set up a trend in a controller. Maybe we're using a table view or a live trend. But I want to look at what that sense medium is. I want to look at what I'm referencing it to. I want to look at the loop output. And for me, if I'm running a chilled water valve or something like that, I want to look at what the valve's doing too. We want to make sure that we're not driving it or cycling it too hard. And maybe I could make some loop adjustments to minimize any of that hunting. The second thing, after I'm set up to monitor, we want to choose some starting points with our proportional and integral constants. And then after that, we're going to tune the loop by first adjusting proportional. And if needed, we're going to add a little bit of integral. Again, every time I make an adjustment, step 3 kind of starts over. I want to make an adjustment, observe a behavior, and then repeat until I get the response that I want. A couple qualifiers here. We want to make sure any of the mechanicals in the system are working properly. It can be very hard, sometimes impossible, to put a loop on top of equipment that isn't working properly. One, because we're not expecting how it's working, but we're putting a Band-Aid over the top of something that maybe isn't going to respond as that loop's expecting. As we're tuning a loop, we want to remember that the system is always changing. So just because you put a proportional value in now and you see the response that you get, doesn't mean that half an hour from now or an hour after the building is occupied or more of my VAVs are open or my discharge air is coming towards set point, I might not get the same response. So again, just be open to the idea that my response now isn't going to be my response later. And the most important thing as we're getting started is be patient. We would always recommend that you wait an appropriate amount of time between making adjustments, so that way you can observe the response and know what you're dealing with. Try to only change one thing at a time. As you see us work through the slides here, our example, we want to adjust the proportional value maybe a few times to get the response where we want it before we add any integral. We don't want to just throw P and I at something and hope for the best and then come back. If we don't get the response that we would see, we don't exactly know what to start if we're changing multiple things at one time. So again, for monitoring as we get started, think live trend viewer. This is especially handy when we're just getting started and we want to see that that air handler DAT start working. If I get the response where I want it, then maybe I would set up some trends in the controller for longer term trending and viewing. I want a trend log that's going to run overnight, and I can come back in the morning and dial into that controller to look at that overnight trend and make sure I've done what I need to do. We talked a little bit already about what to observe. So items related to the loop output, probably going to be in a value object. Any variables or outputs that are running off that loop, and then certainly the set point reference and what my controlled variable are going to be. So a lot of times we get asked, where do I get started, for proportional constants? Again, think throttling range when I'm choosing a proportional constant that I want to get started with. For room temperatures, commonly we see 2 to 3 degrees Fahrenheit. If it's a mixed air or discharge or chilled water loop, we might see a proportional band of 10 would produce a good response to get started. Hot water could be in that 10 to 15, maybe 20. Again, it all depends what you're controlling, but this is a good place to start. After we've determined what the proportional band should be, and it is tuned, some starting integrals for room temperature. Again, think cycles per hour. For room temp, 4 cycles and hours are good, and if we run this through our math to find the constant, that would be 0.08 per hour. And then as we see in the chart, 3, 1, and 1 for some of the more process type variables. But to determine that integral constant, I want to emphasize, think how many times you would want to repeat the proportional band per hour. The more you repeat that proportional band per hour, the faster that integral is going to move the loop up and down. So generally starting, the slower the better, and increase until you get the response you want. I should mention that this webinar will be available, so if you want to pull these constants out later and reference them, you'll be able to do that. So a little bit about what pictures or response that we would get as we start to tune a loop. Again, we're going to start with proportional only and tune our proportional constant first. If we start at the top, a picture there, if you look at the loop, output is in the green and the set point is in the black. If I have too little proportional action, my controlled variable is never going to reach the set point. This means that my proportional constant is too large. Sometimes if someone puts a proportional constant of too large, the loop output may just be stuck at 0% or 10% or something, and it may look like it's never changing. And again, all of this happens generally because the proportional constant is too large. Looking at the middle chart here, we see a loop that's doing a lot of ringing. It's oscillating. It may be going off scale 0 to 100%, but really it's not settling down after several cycles or minutes of continual ringing. What this means is I've got too much proportional action, meaning my proportional constant is too small. For that room temperature, maybe I put a proportional action of 0.5 degrees or 1 degree, and I'm really not giving the loop enough time to deal with the variation in room temperature that would be required to maintain a steady control. So when this happens, I'm going to increase that proportional constant to slow it down and reduce that amount of proportional action. And then the bottom's kind of the Goldilocks number. It's just right. We have some ringing as we come in to a steady state within reason. Some ringing is good and some ringing is normal. The thing to look for is that the amplitude of the ringing is starting to settle down and approach a constant number. One thing to note here is you see as it settles down, we still have that steady state error between the loop output and what the set point should be, and that is normal. So once I do get it to settle down, then I can either tweak the bias to try to draw down the loop output towards the set point, or I can add a little integral to try to settle that steady state error out of the system. Next, let's talk a little bit about integral responses. We're going to assume that we're starting with a properly tuned proportional constant. So again, that top picture is going to show that I have a good proportional term and good proportional action for my system there. If I put in a little bit of integral, again, we always recommend starting small. You may not see a change in response. Your steady state error stays, or it's not being driven down as fast as we would like. A lot of times this might look like proportional only action. And again, that's all because that I constant is too small. So if it is too small, we want to increase that, increase the number of cycles per hour, or increase that integral term to try to get a little more response and drive that error out. So moving to that middle screen or the middle picture, we've mistakenly put too much I action in, or we put too much I in action too quickly. So now instead of a nicely performing response, I've introduced unstable or oscillations back into my control loop. This a lot of times can look like a proportional term that's too low. They look the same, and it results in unstable, or I've got ringing. Again, maybe 0 to 100% continually, or oscillations that don't settle down. This all means that I have too much action and my system can't respond quick enough to get a proper measurement. So when this happens, reduce that I term back out and we should see that loop settle down. And again, at the bottom, here's what it would look like if we have a properly tuned P and a properly tuned or reasonable I value. I have some overshoot. After a few or some number of cycles, I get to a steady output, and I would be right around the set point. So just to review kind of the highlights or the major tips that we would give you to tune those control loops. First one, again, be patient. If especially as we get started, I'm looking at my live trend or I'm looking at my table view, and I put that first P term in there. You know, observe it for 10 minutes or 15 minutes or a reasonable period of time until you know that hey, I have ringing or I'm not getting the set point. I need to make a change. But generally, the more patient you are, the quicker you'll tune your loop. Versus making a lot of adjustments and not necessarily know what to adjust in the end. If you don't know why that loop's unstable, the first thing would be to check the mechanicals and the loop inputs. We want to make sure we're plumbed up correctly on the equipment and configured correctly on the loop. If I'm troubleshooting someone else's loop or a loop that I'm coming back to after a while, we want to see what's configured. Where are we at? If I have an unstable loop and I have proportional and integral both in the loop object, the first thing I'm going to do is either remove or very much reduce the I. I want to tune that proportional constant and then add back the I and tune that. It's very hard to tune both terms at the same time, if not impossible. The third bullet, a good piece of advice, is know when to quit. We can all sit on that bucket and tune loops forever. Know what's acceptable. If I'm a room temperature and I can get it to half degree, I'm sure we can tune it more. But we're going to reach a point of diminishing returns, and so know when to quit or know when to stop tuning is generally good advice. And lastly, this takes some practice and experience, but know what's acceptable. Sometimes proportional only action is acceptable, or proportional plus a little bias. You may not always have to add integral to get a response that's acceptable to the occupant. Proportional integral is probably the most common, but don't be afraid to leave something with proportional only if you're getting the response that you want. So then with that, we're going to have Gene talk a little bit about how we're going to set up Connect and look at one of our loops inside the building.
Hey everybody, I've got Kevin here looking over my shoulder to make sure that I don't go too fast. As Eric's been referring to, we want to do this slowly. I just want to show you some tools that I've got set up here in Connect. First of all, I've got a table view that I've got set, which will refresh like every 3 seconds, and I can watch my values come in from a fan. And we are using a fan that's out in the manufacturing area. So this will be a live fan that's going to be running for us. And the first thing I'm going to do is take out all the integral, and we're going to start with a proportional band that's going to be like 0.05, and we're going to see once what this gives us. And this I'm adjusting on the loop that controls this fan. And I have a trend log set up. This trend log follows the static set point or the static pressure, and it's taken samples every second. So we can see what's happening every second. And then I've got a fan speed trend log, and that's also set up for every second. And as you can see, when I took that integral out of that PI, we should see some things happen. We can see that the fan is getting a little bit out of control. It's oscillating.
So since you've decreased that proportional constant, it would take less air to produce the same response. So that proportional term is moving faster now with 0.05 in there than it was with 0.25.
Yes.
That's what's leading to our oscillation.
So now, and as you can see, this is a pretty low pressure system, but should give you kind of an idea of what's happening when we go to tune a PID loop. Okay, so we've established that we've got some oscillation. So now we're going to change our value in the proportional band. We're going to add about a third to that. So we're going to go to 0.75 and watch and see what kind of a difference that makes on our fan.
Is there a good number to say on how much to change that proportional term each time? You know, a third or a half? What's the guideline to, you know, if I want to start changing that P term?
Well, experiment. Because you've got different equipment and depends on how things are engineered. We don't know for sure what's going to happen. So we just kind of got to put numbers in there to see and get a feel for what's happening.
Yeah, I would probably recommend less than doubling it right away. Just start out slow and see what kind of response you get, and then maybe learn from that response and say, oh, I can double that number and see what happens. Uh-oh.
Well, we have a response.
Yeah.
Shut off.
Well, that's interesting. Did this, oh, I see what happened. I meant to put in 0.075.
Mm.
Mathematician would have caught that right away.
So we've oscillated it into the ground.
Yeah.
So there we were looking for a very fast movement, and it was enough that, you know, we flatlined the output and the loop. So good experience. We have too big a proportional constant, which means we have too little proportional action, and cause that flat line on the bottom of the fan speed and the static pressure.
Yep. That was actually kind of a good example of what happens.
So you're using trends in a controller for troubleshooting. Is it just user preference whether you use that or the live trend in Connect?
That is my preference. Live trend works very well also. The reason I don't use live trend for my own personal preference is because the trend gets so big, and I could probably adjust that in the live trend, but I thought for here, this would work pretty good.
So we're always looking at the time base in the controller trend.
Yeah.
You know, that
we've always got,
128 samples.
right, we've always got 120 samples. So as you can see, that's already the oscillation compared to what's way on the left side when we had 0.05 compared to 0.075. We can see a little bit of a difference already in the fan oscillation.
So the frequency of oscillation may be the same, but the amplitude of that oscillation is really what we're looking to manipulate here. So since we're not really narrowing in on a value, is it time to adjust that proportional constant again?
Yeah, I was just going to give it a little bit of time to see where it's going to, the oscillation was still getting smaller.
So you're telling me to be patient?
Yes, I'm telling you to be patient. The key word, patience. So it looks like it might have leveled off. Yeah, it has. We've got three oscillations that are almost identical. So let's go back to the loop and let's change our proportional band again. I think we're going to try 0.1. Let's see once what happens. Maybe 0.15. Just so things happen a little bit quicker. We'll refresh that. Refresh this. This is our actual static pressure. Come on.
So as we wait for this to load and we watch our this new proportional constant, what the effects of that would be. We have a couple questions. One is if, PID loops are a closed loop. Is there ever a time where you would use open loop control in your building? Yes, there are times that open loop is used. A reset schedule for outdoor air or things like that would be considered open loop because I'm just reading an outside air and I'm putting out a reset value and there's no real feedback loop to change that based on the condition. Sometimes very basic things, maybe a cabinet heater or an induction unit, that might be an open loop kind of control where I just know that again, if my outside air is, 30 degrees, I know that I need to have 50% of that valve output on to get a response. Generally, everything we do, whether it's inside of a loop or reading and controlling a temperature, is going to be a closed loop for most automation functions. So the kind of follow-on to that question that was asked is, can we use the proportional output of a PID to control a floating valve? If so, how? Yes, we can. One great example of this would be controlling reheat in either our Simply VAV or our Conquest VAV controllers. Either of those devices have several different types of reheat output available, whether it's staged or floating, proportional, or time proportioned. All of those are driven off the reheat loop inside of that controller. For modulating control, it's pretty easy to imagine that we're taking that loop and we're plumbing it almost directly out to the output. If it's staged, we're using control basic to determine at a certain threshold, 35%, start stage 1, start stage 2 at 65, turn stage 2 off at 55, turn stage 1 off at 25. Same would be true for floating. If I know my loop is on the high side at 70, 80%, open the valve. If my loop's on the low side and coming down at 10 to 15%, close my valve. But control basic really is the method we're going to use to use non-modulating control off this modulated PID signal.
So now we're going to
talk to him.
Okay, now we're going to add an integral constant.
Wait, So you noticed as we added more P, our oscillation got smaller and smaller till almost it's a flat line. And our static pressure came closer to set point, but we're not at set point yet.
It's up here.
Yeah, it's below the set point.
What is our set point?
0.18.
Okay.
So we now have a stable loop, but we want to drive towards the set point now with the integral.
Mhm. And that's why we're going to put the integral in.
So proportional stable, but I still have error.
Yep. So let's put a 0.1 in here once. See what that does for us.
So as we're looking for this integral response, I kind of want to touch back on why with proportional only do we have steady state error. With proportional only, again, remember that that's a linear gain off of my error. The only way that I'm going to have a PID loop output at all with proportional value is if I have an error. If we think of a room temperature that's tracking out of set point, the farther my error gets from set point, the more loop output I'm going to get until that loop rises to a point where my error stops and my error becomes stable. But I'm always going to have that error between set point and what my input is. If I didn't, you'd see that loop output go back down and I'd be steady at 0. But given a condition of proportional only, I'm always going to have steady state error because it always takes error to create a proportional output.
Maybe I can give you an example of some steady state error or reasons why you would end up with a steady state error. If you think about a room and you're doing room temperature, the heat gain in the room maybe equals the heat loss from the outside. So there becomes this balancing point where the amount of heat you're adding to the room, you're also losing outside, and it's perfectly balanced. The amount of heat you're losing, you're also putting into the room. So your proportional only valve is sitting there at, just a quarter open, and you're in equal, everything is equal. You've equalized the loss with the gain. So now you actually want to get to set point. So you have to add a little integral in there to force that valve closed and raise the room or force it open a little bit more to raise the room temperature up to set point and then close the valve.
So that's what we've got happening here. That's what we were starting to push that point up. We didn't touch the proportional band. The only thing I did was put in integral, and now as you can see, it's starting to push that up towards the set point. Once this thing reloads again. Patience, patience, patience. There we go. So let's put a little bit more integral in there, see if we can push that up just a little bit faster. So let's go to 0.5, see what that does for us.
So as we're waiting for this response, let's talk a little bit. I feel like I rushed this in the presentation a little bit about how we come up with that integral constant that we're going to configure the loop for. How does that loop constant relate to the number of cycles per hour? In the presentation, there was a little bit of blue text that showed you the math. In our control algorithm, the proportional term or the gain is carried through to the other terms. So we need to account for that in how we create that number. So if we think in terms of 4 cycles per hour, we need to divide out the proportional band and divide by 100. And that's how we got 0.08. But again, that math is in the presentation. It will work just the same for other loop values, mixed air loops, DAT loops, but we may be starting with a different number of cycles per hour we want to attain and a different proportional band. But yeah, reference back to the math, and again, if you have the proportional term that creates something stable, we know what proportional term to plug into that math as a starting point for that integral constant.
Okay. As soon as this, yeah, as you can see, we're being pushed up towards the set point.
Without introducing oscillation.
Yep. So we can add, let's do another step one more time. Maybe I'm being just a little bit impatient, but we're going to go ahead and add some more integral again.
So since we're on this configuration page, does the repeats per minute or repeats per hour matter? Is that just a units, or is that actually adjusting the time base that we're calculating on?
It's adjusting the time base.
So the units that you're going to select there for that integral constant are important. Here we're doing static pressure, so repeating on a shorter time base of a minute is something that's proper. If we were doing a temperature, we're probably looking at, whether it's a room temperature or whether it's a discharge air or a mixed air loop, we're probably repeating a certain number of times per hour.
Okay, looks like we've kind of zeroed in on it, I think. We're very close.
It may be a little deceiving in the trend log. The scale keeps changing to the maximum differences or the maximum values in the scale. So actually, as it gets closer and closer to the set point, the smaller and smaller the scale gets. So it looks like maybe the oscillation or the changes haven't changed that much, but they really are compared to the very first trend log we looked at.
Yeah, we're only changing about 1.5% on that fan speed. Let's see what our pressure is now. Come on, you can do it. There we go. Our set point is 0.18, and we are at between 0.13 and 0.14. And it's still going up just a little bit.
And we're stable. So
we're stable.
If we were going to keep iterating through this, we'd have a couple things we could try. I'm going to assume that we're going to approach set point eventually. We have a fairly slow working proportional term and a fairly slow working I term. So it may take time to get that last 400ths up. Here, if I think for our building this works, if I wanted to see something move a little faster, what would I do? Do I adjust my I term or my P term?
I would probably adjust the I is where I would start.
So you'd want to have more I constant and more I term to try to drive that harder.
Mm-hmm.
Okay.
As long as you can not introduce ringing,
yeah,
you're okay.
Yeah. So if I drive that I term harder and I do get ringing, would it be best to keep adjusting the I, or should I go back and adjust my P term to make that loop move quicker and then bring my I back in?
That's what I would do.
Okay. So there you got two opinions, two different ways of doing it.
Okay.
So it looks like we are, as far as this building is concerned, we're, to me, I'm happy where it's at.
So as we wait, we'll give it a few minutes for any additional questions to come through. But we'll say our loop is tuned adequately. I think a couple things we see many people do from this point on is if I want to set up and leave my trend running overnight, maybe to go through an occupancy change, or I know that tomorrow morning, it's going to be colder. I want to see what the response is to that, economizer loop in the morning versus right now. A lot of times we see people set up a trend or multiple trends in the controller. we would set up the same inputs to look at that controlled variable and the input and the loop output. We might see someone take a reading every minute, and then next trend every 5 minutes, and the next trend every hour. So I can see behavior over a longer period of time. But if I need to dive back in and retune something, I can go into those trends with the shorter time base. Question that just came through in the Conquest Series VAV. The application comes with hours defined for reset and 0 in the terms. I should mention that generally, while the controllers all are capable of PID, for ease of troubleshooting, we generally default the terms to proportional only. If there is an I term, then we're probably going to start with something fairly conservative. Again, that 4 resets per hour for temperature, and then you could adjust from there. So the other couple questions we got relate to pausing a PID. A PID, again, it responds because the system is ever changing. The calculation is always dependent on what what's happening in the system now and the error that it's seen since it's been running. If I wanted to change what gets plumbed to the output and pause the loop, my preference would be to do that in Control Basic. It's a little bit of incentive to take your loop output, do some conditioning with Control Basic before you go to the output. If I want to pause it, I can do it there. Maybe that's by writing a value at a higher priority to the variable or to the output. Or if we want to be very fancy, I can write some conditions to look at a BV that say, hey, pause my set point or only update my loops or my output if my loop has changed 10% or 20%, and build some hesitation in that way. But the calculation itself is not something that we would see paused in the real world. Question came in about our static pressure example, and I'll throw this one out for Gene and Kevin too, is in this sample, would this be a good situation where we could bring bias in to get that static pressure up to 0.08?
Yeah, this would be a good example to get that right up there by just adding a little bit of biasing, and that would move it right up to 0.18.
So I would also say that this would this could use some biasing that would give me the response, give me onset point faster. One thing to remember about anytime we're using integral, that integral can add or subtract from the loop value to drive out that steady state error. So if I put bias in to force it to 0.18, that integral maybe would unwind and eventually bring that bias out. So for any loops that I tune or that I would be involved with, I don't generally use biasing anytime that I use integral. Biasing is, for me, is really reserved for proportional only type of actions and systems. Okay. Well, since we're not getting any more questions, the one last thing I would leave you with is that maybe this is a little bit of a surprise, but all of the Conquest controllers do have auto tuning built in. I would caution people, we still need to use good rules of PID loops if we're going to enable auto tuning to know what it's going to do. It follows a very similar process that Gene went through to tune this loop. It's going to start with a reasonable proportional term, and it's going to slowly adjust that to try to eliminate ringing. It's usually only used for slow moving loops. So think of a room temperature or a mixed air. And I'll say for most systems, proportional auto tuning is where I would point you first. Experiment with it. Certainly give us some feedback. When you try to do PI, there's a little too much moving in that system if you don't have it set up right. So I find it's faster to tune the integral a traditional way like Gene showed us, but maybe I would use the auto tune. If I want to start playing with the auto tune, then I would do that on proportional only. So.
Very cool. Well, thank you guys so much for doing that. I'm going to take over here and kind of end us out. We ran over a decent bit, but it was all really good information. Thanks again, guys. Right, guys, so I'm just going to wrap things up here and get my screen up. All right, just a reminder before everyone heads on out, we have been updating our KMC 101 series. So we have a whole series on YouTube in a playlist on 101s for the industry. We did a new video on PID Loops specifically, where you can learn more about that, kind of what we talked about today, and a 101 on some open protocol information. Also wanted to remind everyone, we have a new updated website. So if you haven't checked that out, definitely go out and see all the new and exciting features that we have on it. And it's just a pretty website. So you definitely should be checking that out. I want to remind you that all of our webinars are always on YouTube. So if this is your first time attending the webinars, definitely go to our YouTube channel, subscribe. You'll get pinged and notified right away when our new webinar content and all of our video content goes live, and you'll be the first to be able to access that. So we recommend definitely subscribing there. And you can hit us up on any of our social media channels, including LinkedIn, Twitter, Facebook, YouTube, and Instagram. We would love to connect with you there, so please join in the conversation. And from the Building Geniuses here at KMC, we want to thank you again for attending, and we hope you are all having a wonderful Friday. Thanks, guys. Take care.